Hi everyone, welcome back to the next lecture for acid and base equilibria. In our last session, we have learned some definitions on acid and base. We have Bronsted-Lowry definition of acid, and we have Arrhenius definition of acid. And we also learned about some of the equations that is important, like Kw. We learn about its relationship with pH, pOH, okay? And we have also learned about the properties of strong acid. So now, in this lecture, we are going to learn about weak acid, how to calculate Ka from pH, how to calculate pH from Ka. We are going to learn about weak base, and we are going to learn about ice table. Okay, I will let you know what is ice table later on. Now, if we look at the definition of weak acid and strong acid, it is based on the ionization or dissociations of the acid. Strong acid dissociates fully. It means that it has 100% ionization. It is readily available for its H plus ions to be dissociates. All right, but for weak acids, it doesn't have 100% dissociations or ionization. They only partially ionize in any solution. So there will be a mixture of ions and unionized acid in the solution after each dissociation of weak acid. All right, so weak acids in equilibrium can be represented by Ka equal to concentration of hydronium ion or H plus ion times concentration of the conjugate base divided by the concentration of the initial acid. As we know that when we have any acids, whether it is strong acid or weak acid, we have to create, or we have to come out with the dissociation reaction first before we can carry on with any calculations on acid-base equilibria. So in this case, we have weak acid HA. So HA here represents weak acids. Dissociates in the solution. So we have H2O here. And the product would be the hydronium ion and also the conjugate base. As we know that all acids, they have conjugate base as a product of dissociation, whether it is a weak acid or a strong acid. Okay, same goes with base. All base has conjugate acid as the dissociation product, whether it is a strong base or a weak base. So in this case, for the weak acid, let's say we represent weak acid has SHA, dissociates in water, H2O. The product would be H plus ion or the hydronium ion plus the conjugate base. In all weak acid cases, we have Ka calculation equal to concentration of hydronium ion or concentration of H plus ion times the concentration of the conjugate base divided by the concentration of initial acid. So what is Ka? Ka is constant of ionization, okay, or ionization constant, or acid constant, or dissociation constant. Okay, so simply it always called as acid constant or dissociation constant. So if we look at another simplified version of dissociation reaction is that we have weak acid HA dissociates into H plus ion and the conjugate base A negative. Okay, so when we have A negative here, it's the conjugate base. Okay. Right. So again, Ka is equal to concentration of H plus ion times concentration of the conjugate base divided by the concentration of initial acid, okay, which is the weak acid. So you have to take note of this equation because this equation will be used in many calculations regarding acid and base equilibria. Okay. How do we calculate Ka from pH? Weak acids are simply equilibrium equations. For example, we have an equation just now, Ha representing weak acid, dissociates in water, producing hydronium ion or H plus ion, and the conjugate base. So weak acids are simply equilibrium calculations, and the pH gives the equilibrium concentration of H plus. If you look at the equation Ka equal to H plus concentration times concentration of conjugate base and divided by the concentration of the initial acid, you can see that if you have the information for Ka, you can calculate H plus. Okay, and a concentration of H plus ion is always the same with the concentration of the conjugate base. They always have the same concentration. Okay, and sometimes in the question, you will be given the concentration of the initial acid. So from this information, you can have the answer for concentration of H plus ion as well as the concentration of conjugate base. Okay, so this is how you get the pH from Ka and Ka from pH. It simply comes from the Ka equation just now. Percent ionization is another method to assess the acid strength in the case of weak acid, because in the case of strong acid, we know that it has 100% of ionization. But in the case of weak acid, we know that weak acid dissociates partially, so it is not 100% dissociation. However, it has the equation for calculating the percent ionization for each weak acid. Again, we go back to the equation for dissociation of weak acid. Let's say we have weak acid Ha dissociates in water, and the product is hydronium ion and the conjugate base. So percent ionization is equal to the concentration of hydronium ion at equilibrium divided by the concentration of the initial acid. So this is the concentration of the initial acid times 100%. So this would be the equation for calculating percent ionization in weak acid. Percent ionization of a weak acid decreases as the molarity of the solution increases. So percent ionization has and it is inversely proportional to the molarity of the solution. So if you look at the case for acetic acid is a type of weak acid. Okay. If you look at the case for acetic acid, if you look at the graph here for 0.05 molar solution, 2% ionization of acetic acid is observed. Okay. However, if the concentration increased to 0.15 molar, you can see that the percent ionization decreased to 1%. Okay, so this is an example of the relationship between percent ionization of weak acid and the molarity of a solution. Okay, so if you have higher molarity, you have lower percent ionization for a weak acid. And if you have a lower molarity, you will have a higher percent ionization for a weak acid. Okay. Now, after we have learned all the equations related to weak acid equilibria just now. We have learned that Ka is equal to the concentration of hydronium ion times concentration of conjugate base divided by the concentration of initial acid. And we have also known that percent ionization is equal to the concentration of hydronium ion at equilibrium divided by the concentration of initial acid times 100%. So this is the time for us to apply this equation into solving acid-base equilibria problems, right? Let's look at example 4. We have nicotinic acid, or in short niacin, which is a monoprotic acid. It is a weak acid also. Okay, it has this kind of formula, HC6H4NO2. So the solution is 0.012 molar. So we have molarity for niacin in nicotinic acid. Yeah? We have the molarity 0.012 molar. We have pH 3.39, which is at 25 degrees Celsius. Okay, meaning to say that this is at room temperature. What is the acid ionization constant, which is Ka, for this acid at 25 degrees Celsius? What is the degree of ionization of nicotinic acid in this solution? So we have two questions here. First, we have to find Ka, which is the ionization constant for nicotinic acid. And second question, we need to find the degree of ionization or percentage of ionization of nicotinic acid. Now, it is important for us to realize that when we say the solution is 0.012 molar, this refers to how the solution is prepared. Okay, the solution is made up by what is the meaning of 0.012 molar? It simply means that if we relate it to the equation N equal to mv, 0.012 molar means we have 0.012 moles in enough water to give 1 liter of solution. Okay. So once the solution is prepared, some molecules will ionize. So the actual concentration is must be less than 0.012. Okay. I repeat, let's say we have the initial concentration of the nicotinic acid as 0.012 molar. After ionization, we know that this concentration will decrease so that it will become below 0.012 molar. Okay. In order to provide a solution for the questions that we have just now, first, the Ka for nicotinic acid. Second, the percent ionization. We have to use the ice table. I believe that you have come across the term ice table when you were in the foundation study as well as your STPM. Ice tables refers to I is for initial concentration, C is for change in concentration, and E is for concentration at equilibrium. So if we refer to the questions, we can start constructing the ice table. Okay. Ice table is normally divided into 4 columns. The first column is for you to identify which is the initial concentration, which is the change in concentration, and which is the equilibrium concentration. So this is the first column. Okay, it is for you to define which concentration you are dealing with. Okay, so you have 3 rows under the first column. which is the initial concentration, change in concentration, and also equilibrium concentration. So in the second column, third column, and the fourth column, it comes from the acid dissociation reaction. Okay. In this case, the nicotinic acid can be abbreviated as HNIC. Okay. So in this case, you can write the dissociation reaction as HNIC dissociates in water, and the product would be H plus ion and the conjugate base, which is here. All right. So if you remember, HNIC here is the HA negative. Sorry, HA. This is the HA, the initial acid. Okay, and H plus is the H plus, and NIC negative here is the A negative, which is the conjugate base. So if you go back to the definition for Ka is equal to concentration of H plus ion times concentration of the conjugate base, this will be the A negative, divided by the concentration of the initial acid. All right. So we leave this behind first because we need to go back to our ice table. Okay. So we already have the dissociation reaction. We already have the dissociation reaction. So from the question, we know that the initial concentration for nicotinic acid is 0.012 molar. So we put in the second column, which is the initial acid, HNIC. Okay, we put the initial concentration as 0.012 molar. All right. At the starting point, at the initial point, we know that there is not yet any conversion or any dissociation, no ionization of the nicotinic acid to anything yet because it is at the initial stage. Okay, so we know that the concentration of H plus ion, which is the product, and concentration of the conjugate base, which is also the product, is 0 because no dissociation has happened yet. Okay, so you label here 0 in the second column and you label 0 in the third column, which is for the conjugate base. Now we look at what happened at the at the row for change in concentration. We don't know how much is changing, how much concentration is changing during the dissociation process, but we do know that they change. Okay, so because how much is changing, how much the molarity of the change concentration is unknown, we put it as X. Okay, we know that from our previous explanation, I have explained that when we have dissociation of the weak acid, the concentration will somehow reduced after the dissociation process. So we know that there is a change in concentration, a negative change in the concentration, but we don't know the value. So we put it here as negative X. Okay, negative X represents the change in concentration which reduced the concentration of the initial acid during the dissociation process. Okay, the change is negative X because we know that the concentration of HNIC reduced. So what happened at equilibrium? at equilibrium, you will have 0.012 minus X. So this is the final concentration at equilibrium, okay, after the dissociation process. So what happened after dissociation process to the concentration of H plus ion and also the conjugate base? We know already that the concentration of H plus ion and the conjugate base is always the same. Okay, so whatever comes out from the nicotinic acid or from the initial acid, the concentration goes to the H plus and also the conjugate base. So for the concentration of H plus after dissociation, we put it as positive X because we know that we have new concentration for H plus, which is increased in concentration after the dissociation process. Okay, and we know also for the conjugate base, there is an increase in concentration. Plus, we also know that the concentration of the conjugate base and H plus is always the same. So there would be the same positive X and positive X. Okay, so it's obvious how we calculate the equilibrium concentration. That would be 0 plus X equal to X for H plus ion, and 0 plus X equal to X for the conjugate base. So we have our equilibrium concentration for all the species involved in the dissociation process. We have the initial acid, we have H plus, and we have concentration of the conjugate base. So we go back to the definition for Ka just now. Ka equal to concentration of H plus ion times concentration of the conjugate base divided by the concentration of the initial acid. So we know that here, this would be X, H plus ion. This would be X, the conjugate base. And this would be 0.012 minus X. Okay, how do we get this? We get this from the ICE table, the row for equilibrium concentration. Okay, why we use equilibrium concentration? Because Ka, the definition is the ionization constant or acid constant or acid equilibrium constant. So we know that Ka is representing the weak acid at equilibrium. Okay, so we choose only values from the equilibrium concentration. So substituting all these values in and unknowns into the equation, we have Ka equal to X square divided by 0.012 minus X. In this case, we don't know what is X, but we do know that we have the pH given in the question. Okay, we have pH of nicotinic acid 3.39. It's given in the question just now. So going back to our last lecture on how do we calculate pH from the concentration of H plus ion and vice versa. How do we calculate concentration of H plus ion from pH? It's about the negative log expression. Okay, we know that pH is equal to negative log H plus ion. Okay, but in this case, we have a slightly different situation whereby we have the information for pH, but we don't have the information for H plus. We want to determine what is the information, what is the concentration for H plus ion. So because pH equal to negative log H plus ion. So in order to find concentration of H plus ion, you need to do the anti-log for negative pH. arranging back the equation of pH equals to negative log H plus ion, you get concentration of H plus ion equal to anti-log negative pH. Okay, so if you look at your calculator, I will show you in the camera. I hope it's clear. So if you look at your calculator, if you search for log here, log, okay, log, all right, you press a shift, you press shift log, okay, you press shift log, and then you make a bracket, put your values in, which is negative 3.39, which is the pH just now, and you close the bracket and you um, press the button answer. So you will get the anti-log, which is 0.00041. Okay, so remember, whenever you have questions involving you to find the H plus ion concentration from the information of pH, you have to do anti-log for the negative pH. This comes from arranging the equation pH equals to negative log H plus concentration. All right. Now that you already know what is the value for x, which is 0.00041, you can substitute it into the Ka expression. What is the Ka expression just now? Ka is equal to x squared divided by 0.012 minus x. So just substitute x into the Ka expression and you get this value. Right? So this is X. What is X? X is the concentration of H plus ion. Okay. So here you need to, the question is asking you to find the Ka. So after you substitute all the information that you have, including X, into the Ka expression, you get the Ka, which is 0.012. Okay, you have this as the Ka. Now you find your answer. How do we calculate the percent ionization? Remember, we have percent ionization equal to concentration of H plus ion at equilibrium. So what is concentration of H plus ion at equilibrium? It is X. X is 0.00041. So you have 0.00041 divided by the concentration of the initial acid, which is 0.012 times 100%. So from here, you will get the answer, which is 3.4%. Okay. Now let's look at another example. Let's say we have a typical sample of vinegar solution which has pH of 3. So vinegar is acetic acid. So acetic acid is a weak acid. Okay. So again, we will be using Ka expression as has been discussed just now. Ka is equal to H concentration of H plus ion times concentration of the conjugate base divided by the concentration of initial acid. Okay, so because this is a weak acid, so we are going to use the equation again. It has a pH of 3, assuming that vinegar is only an aqueous solution of acetic acid with Ka of 1.8 times 10 to the power of -5. Calculate the concentration of acetic acid in vinegar. So the question is asking you to find the concentration of acetic acid. So how do you do this? You start doing this by by forming the weak acid dissociation reaction. So let's say here you have acetic acid, you just represent it as HA because we do that all the time. We represent weak acid as HA to be short. So it dissociates into H plus ion and the conjugate base here as the product. So we know that what information that we have? We know that the acetic acid solution has pH of 3. Okay, so we know the concentration of H plus. Why? Because pH is an indicator of the concentration of H plus ion. So we already have the pH. We have pH equal to 3. So calculating the H plus ion concentration is equal to anti-log -3. Okay, so from here you get the concentration of H plus ion. So now you already have information on the concentration of H plus ion, and you know that all the time for weak acid dissociation, the concentration of H plus ion is going to be the same with the concentration of the conjugate base. So once you get the concentration of H plus ion, it means you also get already the concentration of the conjugate base. So you already have this information, you can find the concentration of acetic acid, okay? The weak acid, right? So from here, we know that H plus ion just now is equal to 1 times 10 to the power -3. Again, we go to the ICE table to answer the question. Remember, for any acid-base equilibria problems, you have to use ICE table to solve the problem. Okay, it's the easiest method for you to calculate the equilibrium concentration or to find whatever the question is asking you, all right? So again, like I've mentioned just now, for any weak acid dissociation problems, we need to come out with the dissociation reaction. In this case, acetic acid dissociates into acetate, and the hydronium ion, or you can call it H plus ion as well, no problem, because we can use H plus ion and hydronium ion interchangeably. Okay. Now we have again the 4 columns. 1 column for concentration, 1 column for initial acid, 1 column for H plus ion, and another column for the conjugate base. Okay, so let's say here you have I for initial concentration, C for change in concentration, and E equilibrium concentration. In this case, you don't know what is the initial concentration of the acetic acid, but you do know there is a change in concentration of the initial acid. So the change would be negative Y. What is negative Y here? Okay, let's cancel this X so you don't get confused. Okay, because we just want to show how much concentration is changed. Okay, we don't want the equilibrium concentration. So I'll just cancel X here. So again, I repeat, we don't know the initial concentration of the weak acid, so we put there unknown X for the initial concentration of acetic acid. And we do know that there is a change in concentration. In this case, we put it as negative Y, but of course we already know what negative Y is because we already calculate H plus ion concentration. So H plus ion concentration is 1 times 10 to the power -3. There goes as well for the conjugate base. I'm sorry. This is the hydronium ion, and this is the conjugate base. Okay, terbalik sebut tadi ya. Alright, so we know that the change in concentration has been calculated, which is 1 times 10 to the power negative 3. So we can put here negative 1 times 10 to the power of negative 3. Okay, for the initial acid. So at equilibrium, we know that at equilibrium, the concentration of the initial acid should be X minus 1 times 10 to the power of negative 3. And of course, for H plus ion, it is positive 1 times 10 to the power negative 3, as well as the conjugate base, the acetate, it's also the same concentration. So again, going back to the Ka expression, the original Ka expression is like this. Okay, I have mentioned this, I think, a lot of time today. Concentration of Ka equals to concentration of H plus ion times concentration of conjugate base divided by the concentration of the initial acid. So here, replacing all the values into the equation, we already know, given in the question, Ka is 1.8 times 10 to the power negative 5. So we also know that concentration of H plus ion is 1 times 10 to the power of negative 3. The same goes with the concentration of conjugate base. So we know from the ice table that the concentration of initial acid can be represented by the equation X minus 1 times 10 to the power of negative 3. How do you know this? You can repeat my explanation for the ice table just now. Okay. All right. So from there, you get X concentration of initial acid 0.056 molar. Okay. But it will be different if you want to find the equilibrium concentration. Equilibrium concentration, equilibrium concentration would be, would be X minus 1 times 10 to the power negative 3 molar. Okay, so you know that it's going to be 0.050. It's going to be, this typo, 0.05. Okay, 0.056 minus 1 times 10 to the power of negative 3 molar. So this would be the equilibrium concentration, and X would be the initial concentration. We go back to the question. What is asking us? It is asking us concentration of the acetic acid in vinegar. Okay, so it means we are calculating the concentration of initial acid, not the equilibrium concentration. Okay, right. Now we go to the next example. It's quite simple. Example 6. We have a 0.15 molar solution of weak acid, which is 3% dissociated. So we need to calculate Ka. Okay. So again, we go back to the first step that we need to do every time we want to solve the problem for acid-base equilibria, which is we have to write the dissociation reaction. So in this case, the weak acid is represented as SHA. It dissociates into H plus ion and the conjugate base. Okay, so from here, you need to calculate Ka. Again, what is Ka expression? Ka is equal to concentration of H plus ion times concentration of conjugate base divided by the concentration of initial acid. Okay, we know that the concentration of initial acid is 0.15 molar. This one is 0.15 molar. It's given in the question. And we know that the acid is 3% dissociated. So again, we go to the equation on how to calculate percent ionization. Percent ionization equal to the concentration of H plus ion at equilibrium divided by the concentration of the initial acid. Okay. Now, how do we solve this problem? Again, we go back to the ice table. We have ice table. So for the first row, we have initial concentration. And then the second row, we have change in concentration. The final row, we have equilibrium concentration. So we substitute all the information from the dissociation reaction. Here is for the initial acid, here is for the H plus ion, and here is for the conjugate base. We know that the initial concentration of the weak acid is 0.15 molar, which is given in the question. So we jot down here in the section or in the cell for initial concentration of the weak acid, okay, which is 0.15. And we know that before any dissociation happens, the concentration or the initial concentration for H plus ion is 0. It's always 0. The same goes with the concentration of the conjugate base. It's also 0. Okay. And then what happened during the change of concentration? During the dissociation process, how much is the change of concentration? So the change of concentration, let me cancel 0.15 here so that you don't get confused, because the change in concentration only refers to X, which is the amount given out by the weak acid to the product H plus ion and the conjugate base. All right. So what is the change in concentration? In this case, the change in concentration is given out by 3% of 0.15 molar. Okay, 3% of 0.15 molar is how much? What is the concentration? So you have 3 over 100 times 0.15 molar. You get 4.5 times 10 to the power negative 3. So this is how you calculate the change of concentration. Okay, this is how much is taken out from the initial acid. So this is the concentration of the initial acid. So 3% taken out or ionized from the initial acid. So how much is ionized? It is 4.5 times 10 to the power negative 3. So we put it in the row for change in concentration. So in this case, you already know what is the concentration of weak acid at equilibrium. It should be initial concentration of weak acid minus the change in concentration of weak acid, which is 0.15 minus 4.5 times 10 to the power negative 3. Okay, so this is the equilibrium concentration of HA. And we know that you already have X plus X here and plus X here. So you get the final or equilibrium concentration for both the H plus ion and the conjugate base. Going back to the basic equation for Ka, Ka equals to concentration of H plus ion times concentration of conjugate base divided by the concentration of initial acid. So we know that here is X. You substitute all the values into the equation. X is 4.5 times 10 to the power negative 3. And you have the equilibrium concentration of the acid, which is 0.15 minus 4.5 times 10 to the power negative 3. Where do we get this? We get it from the ice table. How do we calculate it? You can repeat my explanation just now. Okay. You can rewind the explanation. And then after you have substitute all the values, you get Ka, which is 1.39 times 10 to the power of negative 4. Okay, so this is how you do it. You start with calculating how much is taken out from the initial concentration. How much is taken out from the initial concentration represents the change of concentration during the dissociation process. Okay. Let's go to another example. Example 7. We have 1 mole of weak acid HA was dissolved in 2 liters of water. After the system had come to equilibrium, the concentration of the weak acid was found to be 0.45 molar. Calculate Ka or HA. Alright, we go back to the Ka expression. Ka equal to concentration of H plus ion times concentration of the conjugate base divided by the initial concentration of weak acid. So what do we have here? What information do we have here? We have the concentration of acid at equilibrium, which is 0.45 molar. Okay, so we know that we have this information already, but we don't know what is the concentration for H plus ion and also the conjugate base. We don't know it yet. So X equal to how much? All right. What is the concentration of the initial acid? We go back to the information given. We have N equal to 1 mole, yeah? And we have volume equal to 2 liter. So how do we solve the problem to get molarity of the initial solution? Molarity equals to number of mole divided by the volume. So we have 1 over 2, which is 0.5 mole per liter or 0.5 molar. Okay, so this is the initial concentration of HA. Initial concentration of HA. This is HA at equilibrium. Okay. Again, we go back to the the common way or the fastest way to solve any acid-base equilibria problems, which is using the ice table. So for the initial concentration, we know that from our calculation just now, the initial concentration for the weak acid is 0.5. And we also know that we don't have any information for how much change in concentration has occurred during the dissociation process. So we put it as negative X because we know that HA or the weak acid lose some concentration during the process. Okay, so we get that the final or the equilibrium concentration for HA is equal to 0.5, 0.45. Why? This comes from the, it comes from the question just now. It mentioned that at equilibrium, the concentration of HA is 0.45. So if you read the questions carefully, you will know that the equilibrium concentration should be 0.5, 0.45 for the weak acid. All right, now we go to H plus and the conjugate base. At the initial stage, it is always 0. Okay, always 0 for both. And the change in concentration, whatever loses from the concentration of the weak acid during dissociation, it goes to the concentration, it becomes the concentration of H plus ion as well as the concentration of conjugate base. So you put here positive X and also positive X, both for the H plus ion and the conjugate base. And you know that the final or the equilibrium concentration for the weak acid is 0.45 molar. Okay. So you know that the initial concentration of the weak acid is 0.5 molar. So you can calculate X actually because 0.45 here is equal to 0.5 minus X. Okay, so from this equation, you know that X is 0.05 molar. So positive X would be positive 0.05 molar, both for the H plus ion and conjugate base. So the equilibrium concentration for H plus ion and conjugate base would also be 0.05 molar. Substituting all the information, all the values into the Ka expression, you get the answer 5.6 times 10 to the power negative 3. Thank you very much, everyone. For our next part of the lecture, I will explain to you regarding buffer solution. So until I see you in the next lecture, goodbye.